Good afternoon and welcome. Thank you all for coming this afternoon to share time with us to talk about math with the computer scientist. This event is part of several series, a series of meetings that we've been doing really for the last few years. This year we've really been focusing on connecting math with different professions. I'm Janice Reck and I'm from the math department, and thank you very much for coming. And Julie, you want to introduce yourself as well?
I sure will. I'm Julie Sigmund. I'm the director for the Omaha STEM ecosystem, and we're doing this in collaboration with UNO and Bricklayer. So we're excited to do this. This is the third in our math series. We did math at the aquarium at the Henry Durley Zoo, math with an architect at BVH Architect, and this is the third. And I think we'll be looking to do more in the fall. So at the end of this, we're going to have an evaluation form. I'll pass them around, but it really is helpful if you let us know what you liked about this, what you would like to do different, or if you would like to dive deeper into this subject, because this is just kind of a fun little experiment of what Bricklayer is and what you can do in the classroom. There's also some information here if you're not familiar with the ecosystem. So we thank you for taking time and spending an hour and a half with us.
And I have lots of snacks at the back. There's veggies, there's popcorn, there's cookies. Please help yourself, get something that I'd love to see it get consumed. So help yourself to snacks at the back of the room. It's there for you to enjoy. There was also a checkoff sheet that Julie has. You have the sign-in sheet. You want them to check? It's going around. Perfect. We just want to see who's here. All right. And at this time, I'm going to turn it over to Victor Winter. This is Victor. He is a member of the computer science department here, and he and his wife and a couple others have started Bricklayer, which is an awesome program. He's doing some great things. And so I'm going to turn it over to Victor and Jennifer. Thank you.
Thank you very much.
I'll just say hi.
It's my wife, Jennifer. Thanks for coming here. I'm really excited to actually tell you a little bit about what Bricklayer does and what our mission is and how math and computer science relate, because we passionately believe in this. As Janice said, please do eat the snacks, because whatever you don't eat will be served at the next one of these events. By show of hands, how many people here are K-12 teachers? Okay. How many people here are working in K-12? Okay, so are outside, like nonprofits and stuff like this. In K-12 teachers, how many are in elementary school, middle school, high school? All right, okay, cool. So at Bricklayer, we believe that math and computer science is intimately linked. And so the picture here, I think, is an important one. This is Annie Easley from Hidden Figures, the real Annie Easley, not the actress. And if you read up the article about her a little bit, she was actually referred to as a computer. So she was given calculations to perform by researchers to solve certain kinds of problems. And I haven't researched this in depth, but I am assuming that she had tools to help her do her mathematical calculations. So I'm guessing a slide rule, this is back in the 50s. I'm assuming she had tables with mathematical numbers, sine, cosine, or whatever, that had all this predefined calculations that were done for her. So she had tools that she interacted with, and then where the tools left off is where she kicked in. And so that boundary is an interesting one, because it's changed a lot over the years, right? So nowadays, you don't refer to a human as a computer, because we have these awesome computers that can do amazing computations, right? And so the trajectory of, if you look at Annie Easley's story, I would say that what Bricklayer is trying to do is intimately linked with that trajectory of the idea that ultimately that tools that help mathematicians and people that do this kind of stuff, calculation, have gotten more powerful, and how do we interact with those? It's not a slide rule anymore. And so, in fact, this is not an idea that I've come up with. Excuse me, allergy season. a growing number of researchers are kind of recognizing, and have done this for a number of years now, that basically that computer science is more and more playing the role that mathematics did in the old days. And that is, it's providing a formal framework and an exploratory apparatus for the other sciences. And so in that vein, I'd like to kind of, I don't want to read this whole paragraph here, but I want to say a little bit. I think the most important thing I figured out was kind of a meta thing, that the better the tools one uses, the further one can get. Like, I was never good at doing math by hand. And that, that sounds kind of, well, a mathematician wouldn't say that, but you'd be surprised at how often a good mathematician would say that. So if you look at the Marcus to Satori videos and stuff, he will say this: I'm not so good at doing these calculations by hand. And so the idea was that you could get the computer to do math. So there's a certain kind of thinking that's going on here, and somehow you're teaching the computer to do math, and so pretty soon this person was really good at doing math as it relates to physics. Does anybody have a guess who this person is? They got their PhD in physics at 20 from Caltech. So this is Stephen Wolfram. So the idea, right, is ultimately you have these tools that help mathematicians think thoughts and express ideas and describe calculations and carry out calculations, and these tools have gotten immensely powerful. And so then the question is, what kind of thinking goes into interacting with these kinds of tools? Should I turn on my mic? Okay, sorry. It could be the vent. I am using my classroom voice. I'm using my classroom voice, but apparently you're welcome. Okay. Is this on? Just kidding. So you have these giant computers, and people will say, well, a normal person doesn't have access to this, and it's like, well, be careful. The kind of computational horsepower that you have on your smartphone, compare that to what was going on in the NASA project in the 60s, right? So the supercomputer today is the smartphone of tomorrow. And so if you don't think the right kind of thoughts and you want to interact with a device like this, with a machine with this kind of power, if you aren't careful, you will get computationally lost really, really quickly. So there is a math here, there is a thinking here, but it has been tremendously put to the test, how you interact with this, by the tremendous computing horsepower that these devices have. And so ultimately, thank you. Ultimately, the idea is, right, how do you leverage the power of the machine? And what you want, in essence, is you want to write a small program that when you execute it, produces a large number of computational steps. That's sort of the simplest characterization that you can have. And that's what it means to leverage the power of the machine. And in order to do that, in order for that to happen, there has to be a pattern in your program text as far as the computational sequence that's being carried out. So it's a pattern. You have to understand patterns. And this is, so it's all about, I would argue that it's all about discovering and expressing patterns in mathematical terms and in computational terms. And so this is also recognized by mathematicians. So this is Keith Devlin from Stanford University, who said mathematicians are now seeing the study of mathematics as understanding patterns. It's all about patterns. Okay. Turns out that humans are inherently good at understanding patterns in certain kinds of domains. So in textual domains, not so much. Symbolic domains, not so much. But visually, we are really, really good, intuitively, on an intuitive level. And so the visual arts, right? So art is a good domain for trying to explore and understand patterns. DaVinci really, really thought highly of art, and perhaps unsurprising. But what he also said was, in his general introduction to art, his book on painting, he said, "Let no man who's not a mathematician read the elements of my work." So the connection between art and math, if you go to the history of art, is really, really strong. Artists were mathematicians. So now so there's a growing body of knowledge, of research that's showing the importance of visual thinking, spatial reasoning, this kind of stuff, and the impact on the STEM disciplines, in mathematics in particular. So it says that if you talk about geometric reasoning, art students have an advantage over other students. If you want to increase your math skills, improve your spatial thinking skills. They've done this large study where they did a huge group of students, and they basically said that so over 50 years that the best predictor basically of success in STEM is spatial ability. You have neuroscience, right, that basically is starting to look at what parts of the brain are engaged when you're doing mathematical computations, calculations, right? So from these kinds of papers, and there's a bunch of them, this is just sort of a couple of highlights, but from these kinds of papers, there's sort of some highlights are that visuospatial ability is a powerful determinant of advanced mathematical achievement. Spatial working memory was the best predictor of mathematical performance in the 6th grade. And last but not least, you can get better at this. This is an important one. It's not just this innate thing. And not only that, but studies have shown that what you learn is durable and to some extent transferable. They've studied some of this. Durable means you retain it. And transferable means if you're working on similar kinds of problems, they're not too distant, you can apply the skills that you've learned to related problems. So in neuroscience then, even if you do numerical calculation with numbers, you're engaging your visual parts of the brain. So mathematical thinking is grounded in visual processing. And Einstein said that his thought processes were visually based. That's how he described them. So we're in pretty good company, right? This idea, you have DaVinci, the connection between math and art, the spatial abilities, the predictors in STEM and mathematics, lots of research backing this stuff up. And we have sort of, I would say that there's not enough attention to this dimension of how you think that shows up in K-12. Yes, we have art, we have math, but they're kind of siloed. They're kept apart from each other. And math has been around for a long time, and math has been used to solve problems for a long time. And it's been taught a certain way for a long time. But along comes the computer that basically in the span of 50 years makes advances that exceeds the advances in the history of mankind. So yes, in the old days it was okay to have things change once every 100 years. You make a slight change to something and you move forward. But the computer is changing the landscape of this so quickly that it is really, in my opinion, calling into question, are we teaching the right kind of math in the right way? And I just put this QWERTY keyboard up here as an example, because the QWERTY keyboard was laid out for a certain reason over 100 years ago. It was for mechanical reasons that it was laid out the way it was, and then those mechanical reasons disappeared. We don't have hammers in these keyboards, but we still use the QWERTY keyboard. And so people like Conrad Wolfram, and there's a number of others that say, how much time do we really want to spend learning certain kinds of calculations when the computer can do this effortlessly, but we still want to engage. We still need mathematical thinking and this kind of stuff. A couple of other things, just sort of connecting a couple of dots here. This is from the Wall Street Journal a couple of years ago, where Christopher Mims basically said in the future, no profession is untouched by machines. And that is I absolutely believe this. And there's tons of examples that one can give as to how the landscape in the professional world is changing. There are a number of countries that have mandated that coding be taught from kindergarten on. And in the United States, it's a little bit more spotty. There's some cities that have mandated some stuff in a couple of years. There are some states that have sort of had CS needs to be available at least. But recently, in the fall, last fall, Virginia basically mandated it as well from kindergarten on. So this is the first one, at least at this level of requirement. Okay, so that's sort of the landscape. So I believe that within some number of years, every state will have mandated this. This is inescapable. If you believe that, then what should we do now? If we know how the story ends. Oh, sorry, is this?